Yeah, so now the concrete approaches. So first up, adaptive approaches. As I said before, they try to simply adapt the idea of typically k-means in that case to, from batch to stream. And the first one is probably the simple single path partitioning algorithm you can think of. It's called leader. We'll see why. So whenever new instance arrives from the stream, we try to find the closest cluster and or the closest cluster member, and they are called the leaders. Yeah, so we try to find its closest cluster, which is the leader that P fits into. So we assign P to this leader if the distance to the leader is below a given threshold. If it's above a given threshold, we say that P does not fit to its leader, so it creates a new cluster with its own leader, so to say. Yeah. So very simple algorithm. Every P is compared to all the cluster members we have so far. The cluster representatives we have so far. If the closest one is closer than a given threshold, then P is absorbed by this one here. It's the leader of P. If not, if the closest cluster is further apart than the distant threshold, P does not fit to its leader, so it creates its own leader, its own cluster. That's it. Properties, so it's obviously a single pass or one pass fast algorithm, so each object is just processed. We have no prior information on the number of clusters because this is somehow implicit in this threshold here. Results are, however, dependent on the order of examples, obviously. So if the points would appear in a different order from the stream, the results may be different. Yeah? And it's also obviously quite sensitive to a correct guess of this threshold here, which is fixed over the whole time. So even though we may have, for example, a damped or a landmark window model, then this is maybe a little bit unrealistic, but anyway. Yeah? So the threshold is fixed, and it's hard to set, of course, yeah, because you never know how to set it actually. And there is an extension, a little bit more sophisticated, but still simple extension of batch k-means to streams. And the idea here is that we still want to apply k-means, but we apply k-means locally in a buffer. Yeah, so we use a buffer, or also called chunk, that fits into main memory, and we apply k-means locally only in that buffer. Yeah, and then as we see here, we apply k-means on each chunk. So we fill up our buffer with a chunk. Yeah, so the stream is running from left to right, and first of all, it fills our main memory chunk, and then we compute k-means on the first chunk. Meanwhile, the second chunk is running full, so to say. Yeah, then we apply k-means on the second chunk. In parallel, the third chunk fills up, so we compute k-means on the third chunk, and so on and so on. So for each chunk, since we apply k-means, we get k cluster centers. So x prime here is the set of all the k cluster centers obtained from I clusters. Yeah, so we do that I times, so in that case 5 times. So x prime here contains 5 times k cluster centers. K cluster centers from the first chunk, k cluster centers from the second chunk, and so on and so on and so on, and k cluster centers from the ith chunk. And now what you do is you cluster the cluster centers in xy, so in x prime. So you run k-means on the cluster centers from the chunks, and the cluster centers from the chunks are each weighted by the number of points assigned to it. Yeah, so that's a trick to weight or upweight or downweight cluster centers that represent a lot or a low number of points. And then you get a clustering on at least this time period here. Yeah, so you can say, okay, up to here, I want to have a cluster. So you do that up to here in the chunks, and then cluster the chunks. And you can do the clustering offline while you fill up the buffers, the chunks. Yeah, and the stream can go further on, and you always try to create the chunks and then somehow summarize each chunk by applying k-means. Yeah, so the k-cluster centers are somehow some summary information on x1 on this chunk here. The k-cluster centers are obtained from x2 are somehow summary structures or summary information from x2, and so on and so on. And you use the summary information from all those chunks, the k-cluster centers from all those chunks, to compute a final cluster for a given time period here. Yeah, properties, again, it's a single scan algorithm, so the whole thing should work for streams. However, at least the authors claim that it's expensive, and usually as author of a research paper, you try to somehow hide if you think that your approach is expensive. So it's interesting that the authors admit that their algorithm is expensive, but the paper is quite old, so or rather old, so that may be a little bit different, or the view on that may be a little bit different nowadays. But anyway, so in the original idea, there's no aging. Of course, you could try to enhance the whole thing and the weighting of the centers from each chunk, also with a kind of decay. But in the original publication, there is no aging. The cluster model inherently have some limitations. K-means clustering model have the limitations that it has no noise handling. It tends to have spherical clusters or produce spherical clusters of the same radius and stuff like that. And also K is fixed for all chunks. So it may be that in chunk X1, there are only 2 patterns. In X2 there are 4 patterns, but you set probably, I don't know, K to 5, and then you end up in 5 clusters for each chunk. Yeah, so that is also obviously a kind of downsize. So in that case, at least it's likely to be more reasonable to set K a little bit higher, ending up, of course, in a little less in a very fine granular summary here, or in a finer granular summary here, that the cluster centers are summarizing the raw data. So setting up a greater K, using a greater value for K, ends up in a more finer granular summarization, while a smaller K obviously returns a coarser approximation, a coarser summarization of the raw data. So there's obviously a trade-off between being a little bit more detailed, a little bit more accurate on the one hand, and being a little bit more efficient on the other hand, obviously. Okay. Yeah, so that's it for the adaptive methods. And in the next podcast, we will talk about online-offline approaches. See you there.